We're going to get our first exposure to solving exponential equations. I have the procedure there for you, and obviously I don't want to read through that and bore you with it. We're gonna kind of use that procedure and go through it. But basically, an exponential equation is an equation that contains a term or terms which has at least one variable contained in the exponent. So if you take a look down here real quick, starting with example 2, see how you have x in the exponent. Over here you have x and x minus 1 in the exponent. You have 2x, x minus 1, a bunch of stuff in the exponent here. Those are called exponential equations. Now, the ones we're going to do today are pretty basic. They are going to be equations where you can find a common base. So that's what we're going to start off with first in example 1, is just thinking about writing numbers with a different base. And we've done a little bit of this. We've done it with exponents. So let's think about 27 and how we could write 27 with a different base. Now, what you have to keep in mind here, this is very important, guys, very important. They're giving you the number 27. I'm giving you 27. How can you write 27 a different way using exponents, but you got to keep it as 27? You got to keep the value of 27. The only way you can do that is by using a smaller base. And you probably know, you may know, that 27 is a power of 3. So we're going to change 27 to a base 3, because 3 times 3 times 3 is 27. So 3 raised to the third is 27. That's what I'm talking about when it says write each number with a different base. 3 to the third is 27, right? So we changed the base. 27 is 27 to the first. This is 3 to the third. Same number. It's still 27, but it looks different. It looks like it has a different base. It does. It has a base of 3. So this is changing the base. 64, change the base to, we could change it to, we could actually do this, we could change it to 4, and we could raise 4 to the third, because 4 to the third is 64, or 64 can actually be changed to 2, and we could make it to the 6th. 2 to the 6th is 64, and 4 to the third is 64. So that's what we're talking about here. 1/16 can be changed to a 4. 4 to the -2. -2, because, remember, 4 to the -2 would be 1 over 4 squared. 4 squared is 16. And then 16 is also 2 to the -4. 2 to the 4th is 16, but if you want 1 over, it's -4. Remember that negative exponent makes the 1 over. So whenever you see 1 over, it's going to be a negative exponent. 32, we can't use 4, we have to use 2. 2 to the -5. 2 to the -5. All right, 1 over 32 equals 2 to the -5th. So if we are given 1 over 32 in our equation, none of these examples have that, but if you're doing an equation down the line and it has 1 over 32, you can change it to 2 raised to the -5th. All right, so here we go. First thing you got to do is isolate the whatever has the x. We have to isolate that, so we got to isolate the 7x to the -4, or 7 raised to the x minus 4. We have to get that by itself. We're going to add 3. Sometimes you have to do that. And we get 7x, 7 to the x minus 4 equals 7. Well, that's easy, okay? Because 7 is to the first. That 7 is to the first. And I have 7 to the x minus 4 equals 7 to the first. I already have the same base. So if you think about it, I have the same exact base. So all I'm going to do is take my exponents, x minus 4 and 1, and I'm just going to set those equal to each other. X minus 4 equals 1. I can ignore the 7s because I already know 7 equals 7. It's the exponents I'm going to set equal to each other. X minus 4 equals 1. Add 4. You get x equals 5. I'm just going to do it over here. X equals 5. Okay, 5 minus 4 is 1. So to check that, you could say, all right, 5 minus 4 is 1. 7 to the first is 7. 7 minus 3 is 4. So it does work. X being 5 would be the value that would give you 4 on both sides of the equation here. Now this one's different. If I have 36 here, I would need 36 here. I can't just say, don't write this. You can't, I can't just say x equals x minus 1. X does not equal x minus 1 because the bases are not the same. So what you need to do is get a common base. We just practiced getting common bases up here. We made 27 3 to the third. We made 64 4 to the third. We made it 2 to the sixth. All right, and still we kept the value of 64. See that? I kept the value of 64. That's kind of what we need to do here. So how can I keep the value of 36 but make it have a smaller base? Well, 36 is a power of 6. I can write 36 as 6 squared, 6 to the second power. What you do now is you keep the x. It already had an x there, so I have to keep that. We didn't do anything to this side. We're just keeping that. Put that in parentheses. Now apply your exponent law. 6 to the second to the x, we're going to multiply when you raise to a power, you multiply the exponents that are there. So it's 2x. This is 6 to the 2x equals 6 to the x minus 1. 6 to the 2x equals 6 to the x minus 1. So now I can take my exponents and now I can set them equal to each other. Why? Because I have a common base, 6, 6, the same base. So it's going to be 2x equals x minus 1. Subtract x from both sides. You're just solving a regular equation now. And I get x equals negative 1. There it is. X equals negative 1. All right, how about here? Well, 9 and 1/3, they're both powers of 3. So I'm going to change both of them. So here I had to change nothing. 7, 7 was good. Here I had to change the 36 to a 6, and the 6 and 6, we matched it, right? Here, you could make 9 1/3. You're not going to make 1/3 9, but you could make 9 1/3. It's easier it makes more sense if you make them both a 3. Because I know 9 is 3 squared. I know 9 is 3 squared. So I just replaced 9. I replaced 9 with 3 squared. Okay? And I'm carrying down the 2x that was already there. 1/3 is 3 to the negative 1. And then carry the x minus 1 that was already there. Put that in parentheses. So now I raise. That's going to be 3 to the 4x. Apply your rule, multiply, right? 3 to the multiply, distribute. Negative x. And then negative 1 times negative 1 plus 1. All right? So now I have 3 to the 4x and 3 to the negative x plus 1. I have a common base, 3, 3. I can ignore the bases and set the exponents equal to each other. So I'm going to take this and this. Those are my exponents. 4x equals negative x plus 1. Add x, 5x equals 1. Divide by 5. Be careful. X equals, not 5, 1/5. Right there. 1/5. So x doesn't always come out to be a nice number. X sometimes is a fraction or a decimal, whatever. X is 1/5 or 0.2. Last one here. This one looks ugly, but it's not that bad. It's going to end up being a quadratic when we're done. 81 and 27 are both powers of 3. They can both go down to 3. 81 is 3 to the 4th. Okay? To the... And I just carry that down. Put that in parentheses. And then 27 is 3 to the 3rd. 3 times 3 times 3 is 27. 3 times 3 times 3 times 3 is 81. 3 to the 4th is 81. Okay. And then carry, let's see, carry my 5x over 3. This is where you're going to make mistakes, I know. All right, so distribute. 3 to the 4x to the 3rd plus 8x squared. Distribute that 4. 3 to the 15x over 3. 15x over 3. The 3 does not multiply to both. It's like 3 over 1 times 5x over 3. If you do 3, you multiply the tops and multiply the bottoms, you get 15x over 3. All right, so we're going to have, we ignore the 3's, and we're going to have 4x to the third plus 8x squared equals 15x over 3 is 5x. Now I have an equation with exponents, so I need it equal to 0. So we're going to go 4x to the third plus 8x squared minus 5x equals 0. Now I'm going to factor out an x. X times 4x squared plus 8x minus 5 equals 0. Now I'm going to factor more. 2x and 2x gives me 4x squared. It's got to be 5 and 1 if I'm going to get 5. And that works because I could put a plus here and a minus here. I got 10x in here, and then I got a minus 2x out here. So that does factor. You know, we did factoring earlier in the year. You should all be good at factoring by now. So now there's that, and that were my solutions. So x equals 0, obviously. We know that. When we have x as a factor, x equals 0 as a solution. This equal to 0, subtract 5, divide by 2, x equals negative 5 over 2, and x equals positive 1/2. Add 1, divide by 2, x equals 1/2. Okay? So there's my 3 solutions, and of course it was x cubed, so you should have 3 solutions. We know that. Now, we're just going to do this change of base stuff, and we're going to, the compounding interest, we're going to do that in class tomorrow. I want to talk about this change of base formula again, which we learned yesterday in our lesson 43. We were introduced to it. Now we're going to use the change of base formula to actually solve these exponential equations. What happens is sometimes you can't get a common base. So like look at this right here. What about the equation 5 to the x equals 16? Well, 5 and 16, you're not going to be able to get a common base. 16 can go down to 2 or 4, but it's not going to go down to 5, right? So we're stuck. We need logarithms. This is where we're going to need logs to solve. And we're going to do a bunch of these later on, but we're just doing basic ones right here, okay? So can we find a common base for this equation? Well, no, we can't. So I just put no there. And then we're going to use our change of base formula. Here's the recalling of the change in base formula. Why is that applying to here? You have to watch the examples and see how the change of base formula applies. Okay, so, and again, these are the last 3 we're going to do, and then we're gonna move on to compounding interest. So we did these 7. We kind of did these the other day, right? 7 to the x equals 615. So we're going to change a base, convert to log form. The base is 7. Log base 7 of the amount 615 equals x. See that? Equals the exponent. That's log form. Now I can use my change of base formula. Once I have log form, I can do this. So x is going to equal log 615 divided by log 7. Write in your calculator. Log 615 divided by log 7. And I did it ahead of time just to save time. It comes out to be approximately 3.3. Okay? This one here, a little different. But again, 423. We're not going to be able to get a common base. It's not like the other ones where we could get that common base. If this was like 64 or 16, we can get it down to a 4, but not 23. 23 is a prime number. We're never going to be able to get that down to a 4 in our heads. It's going to take a decimal. 4 to some decimal can give you a 23, but not a whole number. So we have to use logs here. We're going to make it log base 4 of the amount 23 equals x plus 1. So one extra step at the end. We're going to have to subtract 1 at the end. All right, so this is log 23 over log 4 equals x plus 1. And then this is 2.2618 equals x plus 1. And then I want just x, and I have to subtract 1. Just subtract 1. X equals 1.2618. So x equals 1.2618 approximately. And then here I have a log base e of 17 equals x. And then we learned that log base e, we learned yesterday that log base e is natural logarithm, ln. So ln of 17 equals x. Again, log base e. Whenever you see log base e, that's a natural logarithm. We didn't really talk too much about why that is. It's kind of a definition you need to know. So ln, the ln button on your calculator when you get to class tomorrow, ln 17 is going to be the answer here. X equals ln 17, which is 2.833. 2.833. All right, and that's going to be it for this video.